to, I would like to define yourself.
Right. So my name is Pakpong Chirarattananon. Right now, I'm an associate professor at the City University of Hong Kong, with the Department of Biomedical Engineering. So I see myself as a roboticist, who is interested in bio-inspired robots and micro aerial vehicles, flying robots, or flapping wing robots, for example.
Mhm.
Yep.
So, first of all, congratulations for the science robotics paper. We will touch on that. But I find what you're doing is very interesting, and maybe I would like to ask you in general, since you have this experience in micro air vehicle and bio-inspired robots. Maybe firstly, if you can give a picture about the challenges, the main challenges when it comes to bio-inspired robot, and then if we go to micro area vehicle here or bio-inspired drones here at this paper already center about.
Sure. So maybe I can begin with a little bit of history. So I was trained when I was a graduate student doing my PhD. I was in the Harvard Microrobotics Lab in Boston, and the project I was working on was the famous Robo project that was led by Professor Rob at Harvard. So the goal, in case you're not so familiar with the project, the goal is actually to create kind of a swarm of insect-sized flapping wing robots. So in a way, they are of course bio-inspired because they are imitating the flight mechanisms of insects, and they are also obviously flying robots, so which falls in the area of micro aerial vehicles. Now, the important thing I think is the question is why would you want to why are you interested, or why would someone be inspired by biology, or why would that be an interesting topic or a good idea to do research? And I think sometimes it is because there are answers to challenging questions that can be found from biology. For example, in the case of the RoboBees project, uh, you will find that in order to create something that is really small and lightweight and to be able to fly, it's actually extremely challenging. If you're interested in that, we can come back to this later. But it's extremely challenging because of many reasons. When you would like to scale a vehicle down, you cannot just train everything and expect it to work the same way as something at a larger scale. And the and that's the reason why you see uh, how insects and birds they actually fly little differently. They actually fly differently. So if you would like to also create something that is small that can fly at the insect scale, you will find that flapping wing mechanism is actually one of a really good solution. And that's also why bio inspiration can sometimes be an answer to engineering problems. Right.
Hmm. Great. So maybe I think we can cover the challenge because I think it will be interesting to tell us what challenges. But before that, I want to ask the paper in science robotics. And okay, so maybe before going to maybe if we can first tell us what's the main problem you're trying to solve in this paper, and maybe we can go for the bio inspiration. Why you choose the seed, Samara, in the design? Maybe you can the problem. What's the main problem here in this paper?
Right. So again, I would like to refer back to another robot, right? So the actual challenge of making an efficient flyer at small scale is due to the inherent inefficiency. Okay, this sounds in going into a circle, but bear with me. So the mechanism of flight, right, that we're talking about is about aerodynamics, meaning the way to fly is actually to create, to propel the air downwards and use direct reaction force to stay aloft in the air, right? So it's about creating the air motion, right? So which is the air is fluid. So everything comes down to aerodynamics and fluid dynamics, right? So in fluid dynamics, there is this number. It's a magical number. It's called Reynolds number. This Reynolds number is basically the ratio of um, inertial forces to viscous forces, right? Meaning inertial forces, it means mass and acceleration, and viscous forces is basically the frictional force, right? Um, so when you scale down anything, uh, the Reynolds number will be smaller, meaning the ratio of inertial forces to viscous forces becomes smaller, meaning there's a lot of energy that is lost in the friction, that is lost as an air drag. That's why small uh, machines or animals or anything, they become inefficient to fly at smaller scales, right? Um, so for example, we find that uh, you cannot scale down airplanes. And for example, wing planes, when they become very small, they become extremely inefficient because of this. As a result of the increased dominance of drag, for example, you will have smaller lift coefficient, larger drag coefficient, meaning you cannot generate enough lift and you lose lots of energy as drag, right? Um, so do you find that Samaras, right, somehow overcome this problem, kind of work around this problem um, by using rotation of their, their wings. And the rotation of their wings are actually creating something that is called leading edge vortex, which actually somehow increases the lift coefficient so that they can fly relatively more efficiently. So let me uh, expand this a little bit further, right? So if you look at airplanes, the main lift mechanism is also the same, is a wing. So wing of an airplane creates move through the air to create lift, right? So in order to create lift, they make a small angle with respect to the moving direction with respect to the air. That angle is called an angle of attack. You can imagine if you have a sheet of paper, right? And if you move it parallel to the air, you actually don't feel much force because the drag is small and also the lift is small. But now if you tilt that paper up a little bit and you move through the air, you will feel that there will be a force lifting the paper up, right? So at a small angle of attack or small tilting angle, that's how the plane flies. Now when you tilt the, the wing of the plane a little bit further, more than say 15 degrees, 20 degrees, you find that the lift becomes smaller. Uh, that's the condition where when a pilot is flying the plane, they don't want to get into. It's called stall, right? Basically the plane will lose lift, and basically everything goes, uh, you know, un, in an undesirable situation. Now, for Samara wings, right? When they actually spinning, when they're rotating, they're actually going through the air at a relatively large angle. It could is likely to be more than, it depends on species and the details, but it's usually more than 20 degrees. But they still have very high lift coefficient, and this is because of there's a vortices that is actually going on the leading edge of the wing. That's why it's called leading edge vortex, right? When they have this, it will delay the stall. It's called delayed stall, meaning it will make the stall happen at larger angle of attack, and meaning even at larger angle of attack, the lift coefficient keeps increasing. So they can actually create more lift when they actually gliding or falling. So if you're not familiar with the Samurai wing, I probably forgot to explain that basically uh, is sometimes it's called helicopter seeds. So basically, it's a seed of a plant that has wings. So when it falls, it kind of rotates and it falls more slowly as a gliding flight. Technically, it's called auto-rotating flight, right? It's one kind of gliding flight, and basically, you see, this study from biology, from physicists, from plants can uh, helps you to find mechanism and a mechanism for flying at small scale. And this leading edge vortex only works at small scale, at low Reynolds number. That's the key. Yeah, thank you.
Great.
Mhm,
Maybe I want to ask you first about
mhm,
how to choose the inspiration. For example, this helicopter seat samurai here is. I'm just wondering when you try to find this kind of inspiration, here insect and here plant, how you choose that. I mean, how you figure out since it's something not everyone could be familiar with. That there's a solution here already we have in nature, but how you come up? Let's choose that mechanism. I mean, how you choose that in the beginning, in which basis?
hmm. Right. So I think the question is how to come into that idea
Yes, and how
from
you
the
choose that?
beginning.
Yes,
Right. Um, I'm not sure whether that's a good answer to that question. However, sometimes it comes from, in many cases, it comes from, well, blunt answer would be it comes from experience and reading more. For example, um, one thing that relates me to this is, for example, as I mentioned, I was working on flapping wing robots, right? And I was uh, somewhat, okay, to some extent, familiar with aerodynamics of insects and flapping wing flights. Now, that you will find that basically all these flyers they are called flights at low Reynolds number, right? Which somehow, okay, which you make use of what people call unsteady aerodynamics or unsteady mechanisms. One of them is termed leading edge vortex that I just mentioned earlier. So what I'm actually saying is, um, one of the key flight mechanism of insects is actually found to be the same thing that samaras or winged seeds use. And so meaning that actually connections here that if you actually familiar with one area, then you probably find something also similar. Find also something similar. However, I think the real challenge is that how to make use of those information that anybody, everyone has access, right? And to create something unique or something new that is also useful, right? I think that is actually a difficult engineering question because, for example, even when you know about these principles, it doesn't mean that you can immediately create a vehicle or a robot that imitates them efficiently because when it comes to robots or machines, there are issues uh, related to, for example, actuations, right? You need to find a way to generate the motion that you want efficiently as well. And if the motion that you want to generate is not totally compatible with the actuators that you have, then the whole thing also will not be efficient. Um, right. So the one example I'm talking about is in the case of the Samara-inspired robot, right? In the paper, uh, you you will see that. we use two propellers on the tip of the wings of the robot. So to elaborate, so we put two propellers, two motor-driven propellers horizontally uh, in a symmetrical but opposite directions to drive the two wings to rotate. Um, an obvious solution actually would be to use one motor, uh, one coaxial motor in the middle of the robot and spin it like a helicopter and spin it like a helicopter. Now, doing that actually would be would not be very efficient because of the mismatch between the the forces generated by the wings and the torque generated by the motors. So it would actually make the entire system become inefficient. So you have to kind of uh, match the system in order to yeah to make more things more efficient as well. So one challenge of Spiral bots is actually not to forget about the constraints on the engineering aspects of the project, for example.
Hmm.
Mhm.
That's a really good point. Maybe I want to ask you in the design consideration. You mentioned, for example,
Yeah.
the mismatch, that if you have one rotor in the middle, it would not be efficient for
Mhm.
energy. And maybe when you try
Mhm.
to look for the actual Samara helicopter seat here, when you look to the material and how they looks like, I mean, the morphology, and also when you try to do that in the lab and figure out which design would be viable to make this work. When you look to this design space, because I don't know, you have a lot of experience, but sometimes it could be messy in your mind. So wild in mind, what I should do here or here, what tactics you think to figure out? Yes, let's do this direction, or you see what I mean?
Yeah. And if I were to expand on that, then I can also say that when you look at the exact configurations of the Samaras, the wing seats, when they are falling, okay, the aerodynamics property, um, you and for example, the wing shape, the wing profile, they through evolution, they are somewhat optimized, right, for that task, meaning to slow down the descent so that they can be blown away uh, like further for their reproduction. So in a way, their configurations, the wing shapes and the mass and everything are pretty well optimized. It might not be perfect, but it's pretty good, right? Now, if we would like to create a robot and then that actually for flying, not for auto rotation, not for gliding, not for slowing down the descent, and we just blindly imitate the wing shape, even at that scale, right? And put that onto the robot. It also will not be a very efficient design because the condition for flying, meaning you actually stay kind of still in the air, and the condition for falling are actually not the same, not exactly the same. Uh, it could be based on the same principle, but they are actually used for different situations, right? So the way we made the robot is we actually tried to understand the fundamental principles, uh, why, for example, the Samrat's wing uh, have that particular profile for that particular task. And then if we would like to apply the same principle, but not for slowing down the descent, but for staying in one place, hovering in the air, then what should the shape of the wing be, for example? And it would turn out to be different. And those two things will not be operating at the exact same condition, for example.
Hmm.
Mhm,
Great. Maybe that's a really good point. Since you already have been working on intelligent mechanism, or I don't, I think it's like for physical intelligence to minimize the control. In that case, when you look to, you say the morphology, or how you see the intelligence in the design, for example. you have been a flying insect or inspired by the bees, and here the Samara, the helicopter seat. When you look to the pattern, what makes these things, a plant or insect, has physical intelligence so that they don't have brain? I don't know how you see this,
Mm,
because that's what you do already. I think the
right.
intelligence and design to minimize the control and sensing and more intelligent in your architecture or structure. How do you see these two things here?
Right. So you brought up a rather interesting point and kind of also um, somewhat, I'm not saying this in a negative way, but it's also kind of a buzzword on,
Mm,
say, for example, artificial intelligence, or in robotics community, we also look at some people call it mechanical intelligence, adaptive morphology, or computational, mo- mo- let me think, morphological computation, for
yeah.
example, right?
Mm,
Talking about how we can use materials and design to facilitate control and maybe stability and to improve to enhance function, right? And that's actually one of a very good point in the field of, say, microrobots or milli robots, or when you want to actually create robots that are lightweight, right? Um, the reason I'm saying it is this. Suppose you want to make your robots, especially flying robots, efficient. What you want to do is you want to get rid of all the dead mass, right? You want to make sure that everything is as light as possible, because anything you carry means you have to expend more energy to support that, right? In the meantime, if you would like to gain function, um, a direct, straightforward solution would be, for example, to add more parts and add more components and actuators, which is actually the opposite of trying to get something to be efficient. So one key is actually to try to make sure to obtain the function you want using as like fewer parts components as possible. Um, so this means, okay, I'm going to give you uh, one example, right? Uh, if you look at Robo, okay, I would like to go back to my previous work, and also not just my work. Robo has been uh, contributed by so many researchers, right? One of the key design of Robo is the original Robo from Harvard, right? That took flight. It has two actuators, only two actuators. Uh, One for controlling each wing, meaning it has two wings, and flapping on the sides of the body of the robot, right? So if you think of a wing of an insect, right, you can think of it as your hand, right? And you uh, put out your hand just like you were gonna do a handshake, right? Meaning your palm is actually vertical. Now, how insects flap the wings is basically it's just flaps the wings or your hands forwards and backwards in a rotational motion. In a rotational motion. So imagine if you waving your hand like that, okay? Because this is the motion created by your actuator. This motion will actually not generate any lift force because it's just pushing the air to the sides. Mhm, right. But and you can do this only with one actuator, for example, because the actuator can create this 1 degree of freedom flapping going back and forth, right? It's piezoelectric actuator. But now, in order to create a lift force, what uh, the researchers did very cleverly, right? I think actually I have to credit my previous advisor, previous supervisor, my PhD supervisor, Robo, I think it was one of his pioneering work, right? That he put a passive hinge onto the wing hinge, meaning it's basically a free hinge, non-actuated, that allows the wing to rotate in the other direction. When I say in the other direction, I'm talking about, for example, rotate about the axis that is formed by your index finger, for example. So your hand now can rotate to have palm up and palm down, right? So when you create the flapping motion, the air will actually push the wing to rotate. And because of this rotation, it generates lift. So meaning actually the wing has two degrees of freedom. One is passive and is driven by only one actuator. And this I'm saying this is the key because you actually have very simple mechanical structure, meaning a wing hinge, a passive wing hinge, that allows the wing to actually have another degree of freedom, uh, to move in another degree of freedom, meaning the wing rotation, not just flapping to create lift for the robot to fly. So that's why you could actually fly the robots with only two actuators. So when it comes to physical intelligence or mechanical intelligence here, uh, we I would say that was one of the example that maybe uh, may not fall exactly into the definition of uh, physical intelligence or mechanical intelligence nowadays, because it does look it looks actually very simple, but it
Mm.
works extremely well, right? So when you work with small robots, all these tricks become very important, and the simpler it is, the better, because they don't go wrong. Because they don't go wrong, they are less likely to break, for example. And in this case, it's also the same that um, the design of the Samara-Inspired robot actually doesn't look identically like a Samara, because a Samara has one seat, and one wing. And in our robot, we have two wings, and that's by design, okay, with two wings. It's basically to simplify the analysis, the modeling, because you have the symmetry, And by using two actuators only, uh, we can also control many things. We can control, for example, in this case, um, the position of the robot, meaning we can place it anywhere in space um, with only two actuators. The interesting part is this, is if you look at quadcopters, for example, they have four actuators, they have four propellers and four motors. Um, you can, in a simplistic way, you can think of four actuators as four inputs. When you have four inputs, you can more or less directly control four outputs, right? So in the case of quadcopter or drones that people know, you can control uh, roll, pitch, and yaw motion. You can think of them as angle, 3 degrees of freedom, and then thrust or net thrust. Okay, so with this four, it can be translated into control of X, Y, Z position and the yaw angle or heading angle. They can be translated, but it comes down to the four things, because you have four inputs, right? Um, so with the revolving wing robot or the Samara-inspired robots, we only have two actuators, two propellers. Um, so, but they oriented horizontally. So what we did was we kind of forego, like we give up control of how fast the robot is spinning in the yaw direction. However, the faster the spin, the more lift it generates. So in a way, if you think the robot, if you imagine the robot is upright. It means that if you uh, propel the propellers faster, drive the propellers faster, stronger, then the robot will spin faster. Then it means you can generate more lift or less lift, right? You can go up and down, for example. If you want to actually move to the side, you can time, okay, the propeller such that, for example, when the propeller is pointing forward, you make sure that it generates more force at that moment, then it will move into that direction. So in a way, we use cyclic control to control the position of the robot. And this probably cannot be called mechanical intelligence. It probably doesn't fit the definition, but I sometimes believe that using tricks like this to improve the control, and with the fact that you have a physical limit because you have only two actuators, but you can still achieve this kind of function uh, by doing some clever tricks, right? Probably maybe I can call this something else, dynamical intelligence or something, maybe, but I think the idea is the same. Is basically you would like to uh, achieve more uh, with in the constraint of your hardware limit, with the constraint of your hardware or of course software, um, and to simplify the control. Another point about this robot is also the fact that I was jumping, right, to directly to position control, but for people in the field of flying robots, they usually would talk first about attitude control or controlling your orientation, because if you don't control your orientation, for example, if you don't make sure that you're upright, imagine if your quadcopter, your drone is upside down, it won't be able to fly. So before it can fly, you have to make sure that it stays more or less upright first, meaning you have to try to control your attitude first. And I didn't say that at the beginning is because for this robot, the attitude is passively stable, meaning if I just give the same commands to two motors, the motors on both sides with the same command, and give them constant command, and I don't have any intelligence, any control, no microcontroller, the robot will still fly up and it will stay upright. It won't go far out from upright because it has what we call passive stability. Passive stability, and that's possible because we have huge wings, and when you put the wings uh, in the right position with respect to the center of mass, the robot becomes passively stable. Um, so the the passive stability sounds it's actually simple than I mean it's complicated, but the concept is also very simple. So for example, uh, if you have a real Samara seed, you can actually throw it from any orientation, and because of the aerodynamic interaction, if you give it enough space, it will actually fall down with the seed below the wings, and it will be spinning. Uh, it's the same as, for example, if you fold a paper to make a paper plane and uh, you throw it up, for example, or you just drop it. If there's enough space for it to correct itself, it will actually go down to the flight condition, to the gliding condition on a paper plane. It means that those systems are kind of passively stable. It has its preferred orientation. But of course, that doesn't happen to everything. For example, if you throw a bottle of water, then it won't always land right side up, for example.
Mm-hmm.
Yeah.
Thanks so much for clarification. Maybe
Mhm.
since the content, I have a few questions for you. If there's something was counterintuitive or maybe surprising when in the design process, maybe in the understanding first of all the here's the Samara helicopter seed, maybe something was counterintuitive to your understanding, or maybe in the design of the actual biospot robot, maybe you can choose whatever he or he
Okay, sure, sure. That's a good question. Let me think about it a little bit. Yeah, yeah, yeah. I mean, at the end of the day, everything has to be what I mean was explained, so everything became like reasonable. But I think at the time there might be a few things that was surprising. Yes, of course. Right.
Mm,
So this is probably not let's say it's it's not counterintuitive, and um, maybe it is surprising, maybe it is not, but I would say it's interesting to know or to find out, right? So you would find that if you look at the robot, sometimes the entire robot is only 35 gram, including a battery, right? But it's relatively lightweight. It's lighter than most commercial drones that are basically autonomous, meaning they can fly by itself. But our robot is actually huge. The fact that it's actually only 35 gram is huge, meaning the wingspan is actually over 2 feet. If you find a 30-gram drone, you'll find that their footprint is probably about 10, 12 uh, centimeter or 15 centimeters max, right? Meaning our robot has huge wings, right? Um, so this huge wings is actually a result of the optimization. From the optimization, we actually had to limit the size of the robot because if we optimize it freely without constraint, I think it would even be bigger than this, and it might actually be even better than this, right? The reason is this: there is something, a quantity that is called wing loading or disloading. Wing loading means how much lift force is generated per unit area of your wing. Uh, for example, yeah, per unit area of your wing. So, for example, if you have larger wings supporting small weight, like lightweight, then your wing loading is low. Right? So it is kind of known that from moment is some there's some theory that's called momentum theory. People use that to describe or uh, in, say examine to explain um, to study propellers to design propellers uh, and to understand the relationship between power force generated by propellers. And when I say propellers and wings and rotating wings, they're more or less the same. But at least according to momentum theory, they don't care. They don't. It's not super rigorous. Momentum theory is something that is rather simplified, but it works well given the simplification. So it has its limitation. But momentum theory says that your actuator disc or your propellers or your rotating wings, right, will be more efficient if your wing loading is low, meaning larger propellers are usually more efficient than small propellers. And that's one explanation, right, why our robot is efficient. It's not the only explanation, but it's one main explanation uh, because we have huge wings, right? So the wing loading is low, right? So when we were doing the analysis, for example, we found that uh, our the wing loading of our robot is 100 times smaller than quadcopters or quadrotors that have similar weights. So 100 times smaller, meaning our wings are basically 100 times bigger. And that kind of explains a lot why we managed to get this kind of efficiency. We also, but at the time, okay, And of course, this loading is also wing loading is also scale dependent. So you cannot just compare. It's not entirely fair to compare uh, different robots of different weights. But if they are the same weight, sure, you can make a comparison. So if you plot out, for example, if we plot out the wing loading as a function, as a function of mass of flyers, maybe we include birds, robots, insects, planes, whatever, right? Um, so after the paper submission, actually after the paper came out, we actually plot out the wing loading versus mass for many things. And of course, we found that for our robots, this loading or the wing loading is much lower than other robots of the same weight. But we also find that the maple seeds or samara seeds, they also have extremely low wing loadings compared to other things of similar scales compared to insects, for example. And at the time, we actually didn't know it. We didn't know that. We could guess that it would be low, but we actually didn't plot it out. We didn't actually make the comparison. So it came out as kind of a good surprise.
Mm-hmm.
Not totally unexpected, but we didn't expect it to be that obvious
Mm-hmm.
either.
That's a great.
Really.
Maybe I want to ask you, just ask you about the challenges you mentioned at the beginning. There's a challenge when you go to small scale, and I'm curious about what are main challenges. Me, for example, I would like to ask you is fabrication, and also do you think sometimes when we try to push the technology, for example, fabrication, still has limitation. I mean, it's just kind of the trade-off. We have something, it's not good, but we're trying to push the other side, but still there's something there. And we in the middle. I mean, maybe in the fabrication, I don't know, you can choose whatever you think. Very challenging. And you can give example what we have, and maybe still there's a trade-off to reach this optimal thing. You see what I mean?
Right. So why um, I have some experience working with say micro robots or milli robots, and I cannot exactly claim uh, that this Samara 30-gram Samara-Inspired robot is uh, at the same scale. Is something that is somewhat uh, larger already, and the micro challenges that you find in some smaller micro milli scale robots do not totally apply here, but there's still some overlaps. It's also something in the middle. So let me elaborate. For example, um, if you would like to go down to say scale of a few grams or 1 grams or even smaller or even just say a few grams, uh, you will have to think differently if you trained uh, in a traditional way. For example, when you think of making robots, people would think of, for example, uh, taking an Arduino, 3D printing a few things, screwing a few things together, for example, to make components, right? Now, a screw probably weighs a gram already. So, I mean, say an M4, M5 screw. So it's not something that you would like to use in robots that are in the order of 10 grams or smaller, and 30 gram is probably on the borderline, for example, right? So, so for example, if you look at our robots, right, you find that it's made the main components, the main structural component is just carbon fiber rod. It's very simple. In a way, it's very simple. We also still would prefer to use off-the-shelf, commercial off-the-shelf components if possible. It's not gonna be, it's not easy to make your own carbon fiber. It's possible. It's not easy, right? But you want to minimize the work you want to do. Um, and our wings are basically just kept on sheet. They're basically uh, some sort of plastic that is super strong and they come in different thicknesses. Um, now, um, but the but one thing that is not very efficient on the robot, that is not very optimal on the robot, is actually the flight controller. Uh, this is because we actually took a flight controller of a commercial uh, drone known as Crazy Flies and just put it on that on our robot. There are lots of functions that actually we don't need. For example, that flight controller is all-in-one flight controller. It has power electronics. It can drive, for example, 4 motors when we actually only need 2. It also has structural components that we don't need, uh, and it makes things a little bit heavier already. But so I think some kind of barrier uh, for people who are actually inexperienced in working with something small, and then they want to make something small, is that they some people, for example, when I train my students, when they coming, and you ask them to design something, they would think in terms of just 3D printing something and or putting things together, screwing things together, right? And that doesn't work when you want to make something very small. 3D printing becomes really good, especially the soft lithography. We have Formlabs and also some cheaper stuff that use LCD resin printing. But but when they become small, their precision is still not there, and say for example the strength is still not there, it's still not nowhere as good as carbon fiber, for example, right? So at smaller scale, there are techniques that based on, for example, lamination, meaning you have, for example, sheets of material that you laminate them together and you make kind of origami inspired pop-up structure. Uh, and we kind of not doing that in this robot because we're not that small, but we also use something we have learned from there. For example, if you compare um, the wings of our robot with uh, with wings of insect scale flapping wing robots, you will find that they actually look very similar. They actually look very similar because basically we just get rid of anything that we don't need. If you look at wings of, say, as lightweight RC planes that people make, uh, they usually make use of balsa wood, for example, or foam, or they sometimes make carbon fiber structure uh, to have camber, meaning they have kind of uh, the profile in the thickness, so the top and the bottom layer are not the same. So they would make carbon fiber structure and wrap something around to create a 3D uh, wing, right? Um, that would weigh something. In our robot, we prefer not to do that. We just say, hey, let's keep this thing simple. We just make flat wings, right? Flat wings traditionally won't work, won't be super efficient for planes, but our flight works at uh, small scale. I mean, it doesn't look small, but the velocity is small. So the Reynolds number is actually still relatively small. It's called intermediate Reynolds number. So it's still in the same scale as large insects. For example, hawk moth, their wings are smaller, but they flap faster. So at the end, the Reynolds numbers are similar. And at that Reynolds number, you'll find that those insects' wings are flat
Mm.
and they work well. They're still efficient. So you find that you can probably make use of uh, those things. And also the fact that our robot has very low disloading, meaning each area per unit area of the wing, it supports really small weight. So meaning it actually doesn't have to be very strong. So it won't have so much problem of bending motion, for example. So relatively, uh, it doesn't have to be super strong, so you can get away with not reinforcing it too much. So you can make the robot lighter and simpler to make instead of 3D printing the whole thing with uh, camber and two 3D profiles, then that would actually, it might work better, but the added weight might not. Uh, you have to balance it with the benefit with the added weight, and at the end it might not be that useful. But we haven't done that, so I cannot say for sure either.
Mm-hmm. No,
Mm,
that's a good point. Maybe the last question, there's two last question here. Maybe the first one about what other maybe something, I mean, other creature do you think is inspiring or still mysterious? How they fly, or is something you wish maybe in future research endeavor that let's understand this creature and you think it may be very interesting. I don't know if you have something in your mind and I don't understand how this thing fly.
Uh, yes. So the question is, can I think of, for example, other creatures
Yeah, and it's
that
still
can be
mysterious to you.
inspiring?
And it's still
Right,
mysterious to you. That's just
right.
how they fly. Yeah. Yeah.
Mm. So, why you can say that I work on bio-inspired robots, and and I can look for kind of inspiration or motivations, um, that way. Now, my this might be personal, okay, but my usual approach is actually not to look at, not to search for something inspiring and try to imitate that, but usually it comes to the fact that I would like to solve some problems, right? And I look for inspiration for solution. I look for solution, and I sometimes find that, hey, those insects, those animals, or those plants have something that could help me. That could help me. Um, the reason I also say this is because I think at the end of the day, it's about, to me, okay, as I said, this could be personal, right? Imitate, you don't want to, I don't want to just imitate something without understanding it well or without justification why I want to do it. If you imitate it, but it doesn't work better than other solutions, then I'm, I don't really want to do that. I'm not so interested to do that. That would be my take, and that's because also there are lots of engineering constraints as well. Um, for example, let's people always say this. For example, we always use DC motors. They're excellent, they're great, right? And you don't actually find something that generates similar motion in nature, right? So it's definitely not bio-inspired, and but it works extremely well, and you create, for example, cars, uh, electric cars from that, and to some extent, we use that everywhere, and it's not exactly or totally bio-inspired. There might be some aspects that people can argue is bio-inspired, but totally is, from a, big perspective, it is not. So to me, I think it's the bridge between principles that you can take from biology and uh, the compatibility with what you have uh, in the technology and in the engineering innovation that make, you know something to function better. You can also, of course, look at biology for limits, or at principles, and to find some limits and to understand why things work that well, why it works well, why it doesn't work well. Now, if you ask me whether what are the things I'm looking for, I think the broad answer would be I'm still interested in locomotion, uh, and for example, you find that lots of these animals, they don't have one function, right? They have multiple functions. For example, birds, they can fly, they can actually walk very well, they can actually jump or hop, and they because in biology there are lots of functions you need to perform to survive, right? And so I think the next challenge in like bio-inspired robots that are small, for example, and it doesn't have to be milli scale, but relatively small, is actually also to be kind of versatile, meaning to be able to do well uh, with many things, not just flying, for example. And I think that is going to be interesting, but of course you will have to compromise, meaning you cannot uh, do well with everything, but let's see how we can compromise by sacrificing as little as possible to have more functions. I think that would be something that is interesting.
Excellent. I don't know if you have any final words like to say for people listening. Any final words like to say?
Right. I think okay. One thing that I consider very important is so I'm one of the people uh, who's still interested in making robots, right? And we want to improve their performance. Now, improving the performance, sometimes these are physical limits. These are related to components, hardware, designs, right? So there are lots going on nowadays with, for example, artificial intelligence, and those are great. Those are really useful. Those are groundbreaking, and I can see that potential. Uh, they can, uh, for example, things like deep learning, reinforcement learning, they can like tremendously improve the performance of robots, right? Um, but at the end of the day, I think we also should not forget that we also still living in physical worlds, a physical world, meaning at the end of the day, we still need physical hardware, and whatever algorithm you put on is there's still limit on what the robot can do in a physical world because of this dynamics of the hardware constraints of the components. Um, so, so I'm just saying that this is also another important aspect. I don't know whether we will get to the point where those, uh, say, artificial intelligence could help us design better robots, uh, not just how it's controlled. Of course, there's some work that they combine reinforcement learning with the robot design, but I think it's still quite early. Uh, and for example, I'm just curious whether we can get to the point uh, where not just we're not talking about just AI beating people in chess or no, not chess. What's that? The is it called Go? Yeah, the IBM. Yeah, but I'm just basically AI not beating people in playing games or making decisions, but whether they can help us with tasks like designing robots or making better hardware as well.
Great. Maybe a quick question.
Right.
I see a lot of books in the background. You said at the beginning you read a lot.
Sure.
What kind of book you can inspire? I mean, you can recommend.
um, there's one book that I like a lot. It's probably not all about bio inspiration. It's about the bridge of. It's about flying stuff. It's called Simple Science of Flight. Let me double check the name in case I got it wrong. Get it wrong, yeah. Simple Science of Flight. Yeah, I think the Simple Science of Flight is basically kind of a popular science book that talks about fundamental concepts of flying. What's fascinating about this book is that it doesn't go very technical, but it actually does work very well even for someone who's an engineer, starting as an engineer, or is interested in flying stuff, flying robots, to understand the fundamental principle. But what's amazing is that it describes everything from a scale of insects. We're talking about small fruit flies that are 3 milligrams, up going up until say Boeing, I mean Airbus A380, that weighs like I don't know how many tons. But what I'm saying is that the physics of scaling is something that is very interesting, and scaling of flying stuff is covered very well in this book, and it gives me, and I think everyone, a very good background and understanding of not just flying, but also the importance of scaling.